Hello, good evening. Can you hear me and can you see my screen?
Yes, sir, it is visible.
Okay. So today, once again, for the maybe fourth week, we will be solving problems on induction machine. Um, Today's problems are mostly based on um, the relation between the maximum possible torque of an induction machine and and the operating and the available torque at any other operating point. How to get relation between them. Before we start, let me just announce this thing about the next class. That today is 18th Monday. Um, Next Monday 25, I am not taking any class. Okay, rather this 25th class has been shifted to tomorrow 19th. So today and tomorrow there will be classes same time 7 p.m. So next class after today is tomorrow 7 p.m. Next Monday 25th there is no class. Again next to next Monday 1st April we will have our regular class. Okay, so tomorrow this time again we will be meeting. All right, so today is the 8th week of this course, and this is the Monday doubt clearing session. I am Saptarshi from IIT Bombay. Um, all right, so I will first start the course as usual by taking doubts from you, although I hardly get any doubt. But anyway, at least for the last few classes, my mistakes have been pointed out by the students. That's a good thing. So any doubt? All right, so before we start, we will first establish some relation that we will using in today's class. It's quite standard. You can use in multiple occasions, but only thing is just remember what all assumptions are there before we start establishing. So as we can see that this PG, air gap power, this is very important quantity in calculating the output power, output torque, speed and other things. Air gap power PG, that is how much power is crossing the air gap going from stator to rotor. Now we have seen this diagram depicting the flow of energy in an induction machine, that first the input power comes to the stator, where we lose the stator copper loss, where we lose the stator copper loss and stator core loss, and the rest of the energy goes to the rotor. So that is the air gap power. So all of our discussions today will be after the air gap, so in the rotor circuit. Now if we draw the rotor circuit, this is the rotor inductance of one phase per phase equivalent circuit, rotor leakage inductance, and this is the rotor resistance. Now we discussed in one class, I think week 6, that circuits of different frequencies cannot have non-zero power flow between them at steady state. So in order to make a unified equivalent circuit for induction motor, since the stator and rotor operate at different frequencies except only for the starting, that is zero speed, we need to have one unified circuit. And in that effort, what we do is we do some mathematical jugglery and we end up with this circuit where rotor inductance is given by x2 and rotor resistance given by r2 by s. So basically this s term takes care of the speed or frequency, whatever, same thing. Now some current I2 is flowing in this circuit, and we know that the torque T, that is given by the developed mechanical power, which is 1 minus S times air gap power, developed mechanical power by the rotor speed omega r. Now uh, synchronous speed times 1 minus S gives you the rotor speed omega r. So if we substitute this, what we get is air gap power by synchronous speed. So simply if you divide the air gap power by synchronous speed, irrespective of the speed, you get the developed torque. This relation is particularly important if you are trying to calculate um, the starting torque, because at that time you get some 1 minus spg, but omega r is 0. So there, this is the only way you can find out the starting torque, air gap power by synchronous speed. Now yeah, so this is what we have. Now suppose we take one case. Okay, so this we discussed some time back, that if you draw the torque speed characteristic of induction motor, that looks something like this at certain value of, so omega increases in this direction and slip increases in the other direction like this. So slip is 0 here, slip is 0 here, and slip is 1 here. There is certain value of slip, we will call that alpha, where we get the maximum possible torque from the machine. But this maximum possible torque of an induction motor is lesser than the rated torque of the induction motor. Rated torque maybe lies somewhere here. Okay, that's why we mentioned that if you do a laboratory experiment on an induction motor well under the limit of the machine, and after the experiment if you draw a torque speed curve, you will get something like this. Basically what you are getting is this part of this curve. Okay, this part of this curve what you are getting. So now suppose we are trying to find out the relation between, so the peak torque, say I write it T P, peak torque, divided by torque at any given slip S. So what is this relation as a function of alpha? Alpha is the slip at the peak speed, and S slip at that speed. So peak torque corresponds to this, slip equals alpha, and some other general value of slip. What is the torque? So if you know the peak torque and this alpha, then for any other speed you can find out the torque. But here you notice one thing, that we are doing everything from the rotor circuit. In other words, um, we are not considering any impedance of the stator side. Okay. So what we have to do is we have to simply find out the expressions of the torque at peak speed. Okay, let us first find out the expression of torque at any general value of slip S. So torque T, as we found out, it is Pg by omega S, synchronous speed. Now what is Pg? Pg is definitely the energy lost in this resistance, because there is no other component that can cause you the loss of, that can cause you any energy loss. So Pg is 3 times. Why 3 times? Because 3-phase induction machine. I squared. When there is energy flow in the rotor, there is no per phase energy flow. Total chunk of energy is flowing. So I2 squared R2 by S times omega S. Right? Now what is I2? 3R2 by S omega S. Keep it separate, and I2 is simply this voltage by impedance squared, I2 squared, so E2 squared by X2 squared plus I2 by S squared. Okay. Now, this is a general expression for any value of slip. Now, what happens at peak torque? Peak torque. Again, we did this last time that torque is Pg by omega S. Okay. Omega is a constant. Omega S is a constant. I think someone's video is off on. Okay. Omega S is a constant. So for peak torque, you have to maximize PG. Maximize PG means maximizing power flow. So maximizing the power flow. What is PG? We just saw. It is the power loss in the resistance. So maximizing that power means making the load resistance, load impedance equal to the source impedance in magnitude. So what we have is this is the relation for or condition for peak torque. So what we get here is S, and as I have mentioned before that alpha we will denote as the slip at peak torque. So slip at peak torque we will write it as alpha. So that comes out to be R2 by X2. So it is a ratio of the rotor per phase resistance by per phase decay inductance. At this slip you get the peak torque from the induction machine, maximum possible torque. Again, this is not rated torque, this is much higher than the rated torque, but by doing any other trick than changing the frequency, you can change this, you can increase this. Okay. All right. Now one more thing to notice here is that what I forgot. Oh yeah. So since I said that it is always at much lower speed than the rated, from this we can say that alpha that is the slip at peak torque is higher than slip at rated. Their speed is lower. Okay. Now this expression of torque, what we had here, if I write it as 1, this is any general value of torque. Here if we replace S with alpha, now S with alpha means this R2 by S is X2. Replacing S with alpha in equation 1 means replacing R2 by S with X2. That gives us peak torque as 3R2 by S omega S times E2 squared by 2 X2 squared. Notice one thing, the E2 did not change. This we have already taken care, because ideally E2 is E2 by S when you have R2 and X2 in the circuit, but we did some mathematical jugglery to make it E2 and R2 by S equivalent. So E2 is not changing here. Now from equation 1 and equation 2, if we try to find out the relation between T by Tp, torque at any slip by the peak torque, what we will get is 2x2 squared just a second. Oh sorry, I did something. X2 squared by x2 squared plus r2 squared by s t by tp. Yes, everything else gets cancelled, and this equation is still very much relying on the machine parameters. We will try to eliminate the machine parameter. What we can do is we can divide the equation by R2, sorry, by x2 squared. And if we divide the equation by x2 squared, what we get is 2 by 1 plus R2 by x2 becomes alpha. So alpha by s whole squared. Just a second, I think I've missed something here. It is coming as 2s squared alpha squared plus s squared. This is not the correct expression. Just a second. It's 3 R2 by s omega s, 3 to s omega s, x2. This R2 by s, we have R2 by alpha is x2, x2 squared.
Sir, in the equation 2, again 3 R2 by S omega S is there, no, sir. In that R2 by S is also we can replace with X2.
That we can, but that anyway gets cancelled.
No,
Both
that is the slip corresponding to the maximum darkness, sir. That won't be
oh,
cancelled.
yes,
So
yes,
the slip
yes.
and that slip equation 1
True,
and
true,
2,
yes. This is
the
alpha.
slips are different.
Yeah, this is alpha. So I have to just write this once again. All the s should be replaced with alpha. This one I missed. So all the s of this, all the slip values of this equation 1 should be replaced by alpha. So then if we do this again, so torque by torque peak, everything else gets cancelled. So 1 alpha by s comes here. And what we have is 2x2 squared by whole squared. Now if you divide by x2 squared, what we have is alpha by s times 2 by 1 plus r2 by x2 is alpha. S squared and multiply by s squared, it becomes 2 alpha s. If you multiply by s squared both, then it becomes s squared s cancelled alpha s by s squared plus alpha squared. Yes, this one is the expression. So I made a mistake here that we had to replace all the s values with alpha from equation 1. This one I did, the other one I missed. So this is a 3r2 by alpha omega s. Okay. So using this expression, what we can do is, if we have the peak torque value and we know at what slip that peak torque happens, we can find out the torque at any speed of the machine. Just keep a note here that stator impedances are here completely neglected. That's how we get this. Okay, so you can derive many things here. Say, for example, T starting, if you want to find out starting, just put s equals 1, so 2 alpha by 1 plus alpha squared. This is the relation between peak torque and starting torque. And you can also see one more thing: if you put s equals 0, that is the synchronous speed, you get 0 torque. So starting torque versus peak torque changes with alpha. Okay. One more thing to notice here is that yes, mm, to look at this expression where we got the peak torque. See, this peak torque does not have a term for the rotor resistance. Okay, this alpha is just a slip. Okay, certain slip at which the peak torque happens. So when we are in changing the rotor resistance of an induction machine, the peak torque does not change. Peak torque does not change. Rather, the slip at which the peak torque happens changes. This curve we drew last time. So it becomes something like this. Frequency is not changing, so synchronous speed is same. We are getting all the curves meeting at this one point. So it is possible to introduce a certain calculated value of rotor torque, rotor resistance, such that you get the maximum possible torque out of the induction machine at the starting itself. One such problem we did last day. How much resistance we need to put so that we can get the maximum torque at the starting itself. Okay. So that's enough formulation for today's problems. We will keep using this, mostly this relation. This relation. So if there is no more discussions, we will directly go to the problems. So once again, I will tell this in the last at the last also. Please notice this thing that our next class will be keep this meeting will be tomorrow, not next Monday. Next Monday there is no class. Next class will be tomorrow, same time, 7 p.m.
Hello, sir.
Yes,
Sir, but this peak torque formula is proportional to R2.
proportional to.
R2.
See, what we have here is R2 by alpha x squared. What is alpha?
Okay,
Alpha is
R2 by
R2 by
X2.
x2. So this is 1 by x2.
Okay. So change in resistance means peak torque will remain same.
Yes. Peak torque will remain same, but the slip at which peak torque happens is R2 by x2. So since we are changing R2, the slip at which peak torque happens, that changes. So increasing, so this side is S equals 1. This is S equals 0. So increasing R2 means increasing alpha. So peak torque happens at lower and lower speed if you keep increasing the rotor resistance. And as we saw in the last problem of last day, that it is possible to introduce a calculated value of rotor resistance to have the maximum possible torque at starting. Okay, I think in one problem we will require this concept today, that this peak torque does not change with the introduction of rotor resistance. So now, just a minute. If we do something, say replace this R2 by alpha x squared as 1 by x2, then what do we have? We have 3 by omega s e2 squared by 2x2. Now x2 is the standstill rotor leakage reactance, which is omega ls. Omega is the rated frequency. Or let me write 2 pi f ls. F is the rated frequency of the machine. So now if I write this, and what about omega s? Omega s is 120 f by p. So omega is also proportional to f. So you see notice one thing here. Notice one thing here, that both omega s, synchronous speed, and x2, they are proportional to f. So what we can see is peak torque is proportional to this if you keep the voltage constant. Or better to say, it's proportional to this. That is E2 by f squared. So now if you keep the voltage same for the time being, voltage constant, then what we can say is peak torque is proportional to this. So reduction of frequency will cause an increment of peak torque. Then how should it look? Should be parabolic. So if we have one like this, starting to have to check. Other one should be like this. So reduced frequency, that means increased peak torque, but reduced synchronous speed. Okay. This I'm not sure what happens here. Not remembering. So everything changes here. The sleep at which this peak torque happens also changes. It's changing frequency. However, with changing frequency, problems are not discussed. At least in today's class. I don't know whether it will come later. All right. So we're now directly going to the questions. If there is any doubt, you can stop me and ask me. So it's talking about 15 kilowatt 3-phase 600 volt 50 hertz 4-pole slip ring induction machine. Again, 15 kilowatt induction machine means at full load you get shaft power 15 kilowatt. Okay, it's not the input power, shaft power. And the maximum torque occurs at 12% of slip, and it is 3 times the full load torque. This they have provided. So what they have said is, okay, we'll look into more. Full load torque, full stop. Stator impedances, core loss, mechanical loss are negligible. Load torque is constant, which draws 15 kilowatt of power. Load torque is constant. I think this is not correct. Anyway, which draws load is constant, which draws 15 kilowatt of power. Answer the following this. So what we first do is make it a habit that you have a problem like this induction machine, you know the frequency, you know the number of poles. What is the synchronous speed? 4 pole 50 hertz means synchronous speed will be 1500 rpm. 2 pole is 3000, so synchronous speed is 1500 rpm. Okay, and also what we know is alpha is 12%. That means what we have is R2 by X2 is 0.12. This we have. Okay, that's all we can extract from the problem. Now we will estimate the full load slip. Full load slip we have to find out. So peak load slip we have. Now we have to find this out. T by Tp, torque by peak torque, is 2 alpha S by alpha squared plus S squared. Now suppose in the place of torque, this T, if I put the full load torque, we will get the value of S. Now full load torque, peak torque we do not know, but what we know is peak torque is 3 times the full load torque. So this is equal to 1 by 3. This is equal to 1 by 3. So from here what we have is S squared plus 6, sorry, not plus alpha squared comes there, so X squared plus alpha squared, and if I bring that back, then 6 alpha S is equal to 0. Okay, we're going to find out S. We already know the value of alpha, so let us, for this equation, not put the value of alpha, make the calculation easier. Let us take alpha also as a constant. Okay, if we do that, we can directly write from here S is minus B, so minus B plus minus root over B squared minus 4AC by 2A, that is minus B plus minus square root of 32, which gives us 3 alpha plus minus, this goes in, becomes 8, so 2 root 2 alpha. So this is the value of slip at full load or maximum torque. Since the induction machine, as of now, we are not connecting any external resistance or something, full load torque is the maximum, the rated torque. So S comes out to be at full load. Slip is 3 plus minus 2 root 2. That's what we get, alpha. Now, as I mentioned here, that full load happens at much at higher speed than the peak torque. Full load torque appears at much higher speed than the peak torque. So this S must be of lower value, than alpha you saw here. Okay, so 3 plus 2 root 2 is greater than 1, so this has to be 3 minus 2 root 2. So what we get is S is 3 minus 2 root 2 alpha. Alpha is given as 0.12. If you put the value, you should get 1, 2.1%. So at 12% slip, we got peak torque, maximum possible torque, whereas at only 2% we are getting the rated torque. So what is the difference? How do I know that this is rated torque, that is peak torque? That is completely decided by the design. So this means whenever the induction machine is rotating at this much of slip, 2.1% of slip, the stator and rotor windings are carrying current for which they have been sized, for which the cross section of the conductor has been chosen for the given type of cooling of the induction machine, so that they can safely carry this much of current. Beyond this, there is a good chance of the insulations or the conductors melting by overheating. Okay. So this is the full load slip, 2.1%. Now the next question is estimate the full load speed. Full load speed, this is basically the rated speed. 1 minus s times the synchronous speed, 1 minus 0.021 times synchronous speed is 1500 rpm, we saw. That is, again, take an idea from here. It's not about just solving the problems and getting the values. Take an idea from here is that although that idea is very prominent from this sleep value also, but here also you can get it, that a machine which can have a maximum speed of 1500 rpm or whose no load speed is very close to 1500 rpm, very close, at full load the speed drops only to 1469 rpm. That is only by 2.1%. This is why again you will see that many people referring to induction machine as a constant speed drive. The speed can more or less, this is the maximum possible speed drop in its operating condition, safe operating region. The maximum possible speed drop. So only 2% speed drop. So more or less the speed is constant. There are ways to vary the speed, V by F control and others. Okay. All right. So now estimate the full load torque. Estimate the full load torque in Newton meter. Full load torque, is there a way that we can know? Okay, so full load power we know 15 kilowatt and full load speed we know. So full load power is given 15 kilowatt and full load speed we just found out 1469 rpm. So from here we can find out the full load torque, which is power divided by the speed, which is, again, do not forget the unit conversion. Everything should be in SI. So RPM times 2 pi is radian per minute by 60 is radian per second. This should be giving 97.5 Newton meter. That is the rated torque of the induction machine that you get at the shaft. For this question, since they have mentioned that mechanical loss can be neglected, this is how much torque is developed. This is how much torque we get at the shaft. Same. Okay. Next part is estimate maximum torque. The question said that the maximum torque or peak torque is 3 times the full load torque. So simply multiply this with 3. This much. Okay, now the next question is starting torque in Newton meter. So we saw that T by Tp is 2 alpha s by, sorry, alpha squared plus s squared. So at starting, if I write T starting by T peak, that means s becomes 1. So 2 alpha by 1 plus alpha squared. That means starting torque is alpha is 0.12 by 0.11 plus 0.12 square times peak torque, which gives you starting torque as 69.2 Newton meter, which is lesser than the rated torque. So the curve of this induction machine looks like this. This is the peak torque, some 292 Newton meter. Starting torque is somewhere here, 69.69 Newton meter, and maybe somewhere here is the rated torque. Rated torque is how much? 97 Newton meter. So this much is the safe operating region where you will be mostly using the induction machine, is around this region. It is possible to go up to this torque. Many a times you will get to see a rating peak torque is this much, but that most of the times or always uh, comes with a time specification also. Peak torque this much Newton meter for this much time, maybe 2 seconds, 3 seconds or something, or maybe even more depending on the design, thermal design. Okay, so estimate the full load copper loss. Now we will need those equations that we derived some time back. That developed power P output is 1 minus S PG, and copper loss is S times PG. Now we have already the P output. Output power is given as 15 kilowatts. So copper loss by output power, if we do, what we get is S by 1 minus S full load. So we have to put the full load slip value. So copper loss full load slip value is 2.1%. 0.021 by 1 minus 0.021 times output power is 15 kilowatt. This is the copper loss at full load, which should be somewhere close to 315 watt. Okay, some message came. Okay, so we'll move to the next part of the question. Estimate of the ratio of starting current to full load current. Starting current to full load current. How would we know starting current to full load current? We have the circuit to us. This is the circuit. X2R2 by S. Although the question says that there is no impedance here, and here. So we can simply solve this circuit. We know full load value of slip. X and R are known. Okay, so they have not given X and R. Currents we cannot find out by solving the circuit. We do some other way. Okay, this is not a way. So what we can do is we can find out in terms of torque. So starting torque we know, and full load torque we know. So let us see if we can do something in terms of torque. Torque is 1 minus the torque power. So torque is PG by omega S. So PG is, as we know, 3 I2 squared R2 by S omega S. Now if we write starting torque by full load torque, since that's all we have, what we have is I2 starting squared times R2 by starting S is 1, so only the omega S, times full load slip is 0.021 times omega S by 3 times I2 squared at full load times R2. So here we get is I2 squared, everything, what else get cancelled? R2 gets cancelled, omega S get cancelled. Where did the 3 go? 3 should be here, yes. 3 is only for the 3 phase, so this should get cancelled. 3 get cancelled. Everything else is here, so I2S squared times 0.021 by, yeah, now we have the relation. So starting current by full load current, we already have it here, so it should be starting current by full load current is square root of starting torque by full load torque. Okay, let me write the, like it as a slip once again. Full load slip by full load slip, just to write the expression instead of values. So now we can put the values. Starting torque was how much? 69.2 and 97.5. And full load is 0.021. Just tell me whether it is coming as 5.87. Okay. See, in this problem, what we did is starting torque. Since starting was involved, we simply put corresponding slip equals 1. We could have done a more generalized way. Can you make out from here that had we not put, I'll just write with some other color. See, if we write S slip at starting, SS here, then that comes here, and that comes here. Sorry. So this is a more generalized expression that current at any slip S, rotor current at any slip S by the rotor current at any other slip. So let me write it in this fashion. So rotor current, say I is rotor current. Okay, I'm not writing. So I at some slip S1 by I at some slip S2, that is the ratio is equal to torque at S1 times S1 by torque at S2 times S2. This is a more general expression. Why I am doing this is, like, next problem we have a similar thing. So instead of going through all this once again, we can simply use this expression what we have just derived. Can we write this? This problem does not consider any impedance from the stator side. That's why rotor current is the machine current. Had there been a magnetizing branch, we had to calculate, we had to consider that also. Okay. So now we have to find out the ratio of current at maximum torque. Say I write current at what to write. So we call this I2. Not we can call it maximum torque. Not to the power. Current at maximum torque versus current at full load. This is just maximum torque, which is some 200 Newton meter, 292.5. Which appears at a sleep of 12%. And full load torque is some 69.2. Appears at some 0.021%. Sorry, 2.1%. This should be something close to 4.2. 4.189, yes. Okay. Try to derive and remember some of this. Not remember if you are not going for an MCQ exam. Just general expressions are better, but whenever you are doing general expressions and all, make sure that you do not forget the assumptions behind it, the basis from where the calculation starts and what all assumptions it takes. Okay. So for definitely in this case, we can call this as a ratio of the machine current at starting and full load or whatever, but not if the stator impedances are considered. But once again, even if the stator impedances are considered, these expressions can always be considered as a ratio of rotor currents, right? Rotor, you can always call them as rotor current ratio at these conditions. So do not forget those things. Do not just remember these as shortcuts or something. Full load efficiency should be coming very high because all the losses except rotor copper loss is neglected. So that is the full load output power by output power plus loss. So output power is 15 kilowatt by 15 kilowatt. Do I need to multiply it 3 times to find out the rotor copper loss? See, rotor copper loss calculation we did from the point of view of air gap power, PG. So whatever you get here is for all the three phases. Do not make a mistake of multiplying a 3 here. 315. And the efficiency comes out to be 97.9%, which is unusually high for a three-phase 15 kilowatt induction machine. The reason I told, because stator losses are all neglected. Stator loss means stator copper loss, stator core loss, and mechanical loss, all are neglected in this problem. That's why you are getting such a high efficiency figure. This you should not expect from a 15 kilowatt induction machine. If it gives 90 to 92%, that is very good, and maybe it may give less than that also. Okay. Now we'll go to the next part of this problem. Consider the slip ring induction machine mentioned above. They mentioned slip ring because now the rotor resistance is made 4.5 times, because they are adding a rotor resistance. Squirrel cage, obviously you cannot add rotor resistance. That of the original value by inserting external resistance. Do you know how resistances are inserted? Generally in our lab, what we have done is 3 terminals come out. The slip ring induction machine experiment, 3 terminals come out, and there are rheostats. External rheostats we connect and short circuit. And short circuit like this. Now when we are changing the rotor resistance, see 3 rheostats are mounted on the table or whatever. Their wipers maybe are like this. Using our hands, we try to move all 3 of them together so that the rotor resistance is equal. Now sometime it may happen that maybe varying friction or something, any manual error, you cannot move the wipers simultaneously, so there is an unbalance in the rotor resistances. So to avoid that, sometime what is done is, say 3 rotor terminals come out after the slip ring come out, and what you do is you feed them to a 3-phase diode bridge rectifier, and what you get here is a resistance, sorry, is a DC, and here is a switch and a resistance. Now this switch is not a mechanical switch, it's a semiconductor switch. So you can understand that so what is the equivalent resistance seen from here? From here, if this is R, then the equivalent resistance seen from here should be, suppose if I keep it closed, then complete R. Keeping it closed means S equals 1. It is D times R. No, not D times R. Wait. Resistance does not become 0 here. Sorry. Okay, good that I drew it like this. It's not like this. Switch is parallel, and the resistance Req that we see from here is 1 minus D times R. So when you do not want any resistance at all, so when you want to make the R external equals 0, that means when you simply want to short circuit the simply want to short circuit the rotor terminals, you want R external equals 0, what you do is you keep D equals 1. What is D? D is duty ratio. D is duty ratio of the switch. When it is 1, switch is closed. When it is 0, switch is open. And this time is the on time, and this time is the time period T. D is the ratio of on time by time period. So if you keep it completely closed continuously, that means it's always closed on. So D is 1. You are simply short circuiting the rotor resistance. And if you need some other value of resistance, you give some value of D and you get some Req. So since 1 minus D is less than 1, you get Req less than R, and the maximum possible resistance you can have when you completely open the switch. So R external equals max if you want, that is R, that is D is 0. This switch S is always open. Okay, in this way you can ensure that there is no unbalance in the rotor resistances. Okay, since you have to just you have to only
So like this should be
control
some SCR or IGBT. This diode will work.
not SCR, what diode bridge.
Yeah, symbol is diode, na?
Here diode is enough. Why make it complicated using SCR?
No, but diode, how will I make it like controlled on off?
I'm not controlling it. It's a simple rectifier that is converting the AC to DC. I'm controlling this switch S to control the load resistance.
Okay.
The equivalent resistance that the rectifier sees is given by this. This is done to avoid any unbalance in the rotor resistance.
Okay, okay. Yes, sir.
So first I drew a wrong circuit. What I did is I drew like this. Can you tell me why this is wrong? I drew it from a thought process that how can I short circuit the diode bridge? But then I realized that it is wrong, because suppose you are using this and you keep this switch open, or maybe whenever you are switching this at certain frequency, that means at certain time you are breaking the rotor circuit. The rotor current does not flow at all. That means continuously, periodically, your rotor current is getting 0. That means you will be losing torque if you do this. So this
Yes,
is
sir.
wrong. Here you are either letting the current flow through the external resistance or through the switch. That means rotor current is never cut. So this is wrong. This diode bridge can be short circuited because by default, or by not by default, we keep the rotor winding short circuited. Yeah, by default, if we do not want to connect some external resistance. Okay. All right. I will remove this circuit. This may cause confusion to others who have not referred to the lectures. I mean this class. Okay, we diverted a little bit. Question was estimate the slip in which the new maximum torque will occur. So we'll write as alpha prime, which is R2 prime by x2, it has been made 4.5 times. So 4.5 r2 by x2, that is 4.5 times alpha, which gives us alpha prime is 4.5 times. It was 0. Sorry, 1 2 0.54 you will get. So you see, now the maximum torque is occurring at much higher slip, means much lower speed. Refer to this graph. So this is increasing resistance. Maximum torque is now occurring at much lower speed, much higher slip. That is evident from this graph also, the way we draw. Since we talked about rheostat, let me tell you one more interesting thing, interesting practice of drawing.
Sir, one thing, only one resistor is required.
Yes, because I am feeding, see, this is coming from the rotor, right?
That is a beauty actually. One resistor is required.
Yes, the rotor is just seeing this as a load. I told this in some, I think last class itself, that the rotor does not know where that energy is getting dumped. You can even send it back to the grid. Slip power. So here, to make the load look balanced at all point from the rotor point of view, we do this. We can do this. You can have, instead of this silicon device, you can have a rheostat also here. Question is how to draw a rheostat. Okay. Suppose this is a rheostat. Let me draw a little longer. A rheostat, okay. Like this. I can draw the wiper in this fashion, in this fashion, in this fashion. So when I am drawing a circuit, maybe in a technical report or somewhere, in what way should I draw the rheostat? You tell me. A, B, or C? Let's call this point P1. Let's call this point P2. A, B, or C? What should I draw?
Yes, sir.
Anyone else wants to comment on this? The answer is neither A nor B nor C. It depends on how you want the rheostat to be at the starting of the experiment. Okay, because maybe someone who knows how to make connections but does not know how the thing works, he will simply look at your drawing and make the circuit. Now you have to give the instructions through your drawing that how the rheostat wipers should be positioned when you are making the circuit. Say for example, you are doing an experiment on speed control of DC machine. Okay, so this is armature, and this is the how does it look? Just a minute. Yeah, this is the rheostat settings to control the armature voltage. Here the supply voltage comes V, wipers. This wiper goes here, this wiper goes here. Okay, now how do you want to start the DC machine, you want to start the DC machine with minimum voltage, minimum armature voltage, that there is maximum resistance should be there on the rheostats. So when you are drawing the circuits, the wipers should be here and here. Wiper should be here and here. So someone who is making the circuit knows that when I'm making the circuit, before turning the switch on, I have to keep them at the maximum possible resistances. One more thing is there. There is a field. Field. Now field current, you want full. You want full field current. So this rheostat should be at short circuited position. So one knows that when I'm making the circuit, the armature rheostat should be at their maximum resistance position and the field rheostat should be short circuited. If you do not do, there will be a catastrophe in this experiment. What will happen? If you keep it somewhere here, the person also keeps the wiper somewhere in between. You turn on the machine at a very low voltage, the machine starts spinning at an extremely high speed because reduced field. This thing actually happened to me. I just started engineering that time, and I was under an impression that every resistance should be at their full value, maximum value, so that we get the minimum current in the circuit. So first experiment was this DC machine circuit. Armature resistance I kept maximum, field resistance also I kept maximum, turned on the circuit. And the machine started spinning like anything. I got scared very fast. Then we found out that the field current was so low, the machine started spinning very high. Okay, so this is the practice. That is how you should draw circuits. Okay, that thing happened around maybe 8.5 years back from now. Okay, so a lot of discussions did not solve the problem. Estimate the slip at which the new maximum. Oh, we did this already. This one. This is the slip at which the new maximum torque will occur. Estimate the new full load slip. Full load slip. Okay. So torque at full load by torque at peak, we know 2 alpha s by alpha squared plus s squared. Now just see one thing here, something was given in the question. Load torque is unchanged. Load power may not be unchanged. That's why I told you that this is wrong. They said load torque. Okay, load torque is constant. No, this is not wrong then. I thought power. Load torque is unchanged. Load power is not unchanged. So TFL is still what we had before. And peak torque, we saw that introduction of rotor resistance does not change the peak torque. So both these values, full load torque and peak torque, is same as before. So we can still write 1/3. It was given this ratio as 1/3 in the last problem. They have said load torque is same, and we know that peak torque is same because introduction of rotor resistance does not change the peak torque. So this is still 1/3. So we solve this as something 3 minus 2 root 2, 3 minus 2 root 2 s. What is? Not s, alpha. So this equation remains same, the solution also remains same. S comes out to be 3 minus 2 root 2 alpha, alpha primed, the new alpha. Alpha primed is something 0.54. So 0.54 times this should give you some 9.26. Percent. Okay. Now see one thing, I will redraw the graph here again for a better visualization. Torque speed, say this was before the introduction of the rotor resistance. This is the after, say something like this it looks like. See here, say this is the full load torque. So previously full load slip was somewhere here. Now it is somewhere here. This was 2.1%, and we can now see that it is 9.6%. Right. So the graph, what we are doing now is in agreement with each other. The graphical way, we're not doing the graphical way, but the graph is matching with our calculation. They're consistent. Okay. Slip is increasing, speed is reducing for the full load. So when the motor is loaded by the same load torque, the speed what we are getting is low because there is resistance in the rotor circuit. Okay. Now estimate the new full load speed. Full load slip. This is the full load slip, right? Yes, full load slip. So full load speed, synchronous speed does not change because frequency is same. So full load is simply 1 minus s times synchronous speed is 1 minus 0.0926 times 1500 rpm, which should give a value of 1361.02 rpm. Okay, estimate the new mechanical power. So what happened is our speed we know, and torque they said it remains constant. So torque we can bring from the last problem, not starting torque. Full load torque was 97.5 Newton meter. So new mechanical power at full load is torque times speed converted to SI unit into 61 is, this should be some 13896.34 watt. So introduction of the rotor resistance has now reduced the output power. It's delivering the same torque, but at a reduced speed. So the power has reduced to 13.8 kilowatt. Rated was 15 kilowatt. Okay. Now estimate the new full load rotor copper loss. Again, the same way we will do. How did we do? S by 1 minus S. So output is 1 minus SPG and copper loss is SPG. Good thing about these problems is that they ask you step-by-step questions so that you can write the answers step by step. That is, they guide you. it may happen in your university problems. I don't know how the problems of this course is set in the final exam, that out of the blue they'll just give you the initial data. Out of the blue they ask you estimate the efficiency. So you have to know the flow, you have to go in this flow to step by step find out the things and find out the efficiency. So things are easier for us here. Copper loss is S by 1 minus S output power. S is definitely the operating slip, full load slip. Full load slip is 9% here, 9.26. So 0.0926 by 1 minus 0.0926 times the output power. I'm not writing it again. Output power PO. This should give, what is it giving? Can you just tell me? Did not do this. How much is it coming? Okay, let me do 0.092 is 0.0926 by 1 minus 0.0926 times 13896.341418. Increased a lot. It was 300 something. 1418. What? It was 300 something. Definitely rotor resistance has been introduced, so it will increase. Now see, since we had this discussion how to draw, here also for this circuit, if you instead of this silicon device which is being switched at some frequency, maybe 5 kilohertz or something, or maybe even lesser, we might not need such high frequency in this case. No, 5 kilohertz is not high frequency. Maybe it's good for this case. What I'm going to say is how to draw the rheostat if you are using in this case. So you would want low stator current and high starting torque at the beginning. So maximum resistance you would want. So for this experiment, you would want to draw the rheostats like this. These are things actually we used to follow when we were writing our laboratory reports during BTech times. These things were very carefully observed by the professors. So this is how we would draw things. This experience was very scary. It was a 1500 RPM, 1500 2000 RPM DC motor. Suddenly it sped up so fast and I could feel the tables and other things vibrating. It was my first experiment in the basic lab. By lottery system, I got the motor on the very first day. Anyway, luckily I was not thrown out of the lab that day. Estimate the new starting torque. So what we have starting by peak, sorry, peak torque did you calculate here? Oh, peak torque is same. Peak torque remains the same. So 2 alpha by 1 plus alpha squared. new alpha, okay, not the old alpha. So new alpha is how much? 5.4, so yeah, 0.54. So starting torque is peak torque. Peak torque is same, 200 something. How much was it? 292.5. So 292.5 peak torque times 2 alpha prime, 2 times 0.54 by 1 plus 0.54 squared. This should give you the starting torque. 244.58 Newton meter. Again, we will refer to the graph. See, starting torque has increased, should increase, this graph says. We had starting torque of some 60 or 90, 69 Newton meter before. Now it has increased tremendously. Not to the scale, but this graph is giving us an idea that increasing resistance is increasing the starting torque. It is possible to have a calculated value of resistance when you have a curve like this, maximum possible torque at the very starting. And the current also reduces. Starting current also reduces. So this is one way of induction motor control. Only thing is, this is lossy. You are losing the resistance in the losing the power in the resistance. So if you do not want to do that, extract the power from the rotor, feed it back to the grid, control the power. You get everything. Means you get full starting torque, you get less power, less current at the stator end, and you have no loss. Ideally no loss, practically there will be some loss. One thing that I drew in the last class at the very end, this Sharbia's drive, I directly connected this to the grid with inductors, but there may be problems, not problems, there may be voltage mismatch, which is very likely. So common practice is to use a three-phase transformer here. Okay, the transformer leakage reactance will act as a series resistance to this three-phase transformer. So this is what I was talking about. Just give it back to the grid in this way. From the stator and rotor side, it makes the same effect as connecting a resistor to the rotor, but there is no loss. So that is why power electronics plays a lot of role. Nowadays, we cannot think of drives and power system without power electronics. Okay, estimate the new full load efficiency. We know the full load rotor copper loss. We know the full load output power also. Power has changed. It's no more 15 kilowatt is 13896 watt. So 13896, let 13896. I'm not writing the decimal. 96.1 plus 418. Mr. Dinesh is continuously giving the answers in the chat box, although I cannot refer to it. Thanks for your cooperation. 90.7. Since I'm looking into something else on the other screen. Okay. Hey, what did I do? P output? Final answer question is last question for the day. Estimate the new ratio starting current by current at full load torque. What is happening, man? Starting current and current at full load torque. Let me make a mark here. We still do again. We did it some time back. Some general expressions we found out like this. So it's direct. Direct means starting current by current at full load is starting torque sleep at starting, which is 1 by full load torque times sleep at full load. I hope we have all the data. Starting torque is 244.58. 5.24 is the answer. Okay, I will just write. And full load torque. Oh, full load torque they said did not change. So 90 point something it was. How much? 97.5. Full load sleep did change. It became 9% or something. 9.26. Is this what gives you 5.2? See, try to do these things, okay? A general expression you try to find out. Means, I'm not saying you have to remember this and all. While solving the problem itself, you keep finding the expressions, general expressions. Maybe at some other stage of the problem, you need not do the same calculations once again. See, here it became much easier for us. Okay, so that's all I have to deliver for today. Now, if you have any questions, I will try to answer. Next day, I don't know. Do you still have induction machine next day? Oh, I will repeat this once again. Next class is tomorrow. Okay, I am going to a conference next week. That's why I have preponed the class to next day. So tomorrow is the next class, 7 p.m. same time. Today is 18, 19th is tomorrow, 7 p.m. same time. And next Monday we are not taking any class. 25th we will not meet. Next to next Monday, 1st April, will be our next to next class. Okay. From then onwards, again every Monday we will have classes. So tomorrow also we are meeting. What do we have? Tomorrow is 9th week. So 2/3 of the course is complete by now, 66%. Oh, again induction machine tomorrow. I think some testing of induction machine or something is there. Short circuit, open circuit test. Sounds very interesting to say. Short circuit test of induction machine. Induction machine is by default short circuit. How do you do a short circuit test on induction machine? Anyway, so just a jugglery with words, nothing else. Basically, if you stall the machine and give voltage, that is short circuit for any machine. Yes, block rotor test. Short circuit, what I meant is resistance is R2 by S, right? R2 by S. Now when you are what to say, you get the minimum value of this resistance when you have the maximum value of S, that is S equals 1. You get the minimum value of resistance, that is at standstill. You block the rotor, give some voltage, very low voltage, until the stator draws the maximum current. Maximum current means rated current, not maximum, rated current. Since it is the minimum impedance on this side, looks like a short circuit, which is equivalent to short circuiting a transformer. Actually, if you see something like this does not change. What changes is this. At standstill, basically this is short circuited. Short circuited. There is a short circuit test. This resistance has several things. Induction generator, if you see, this is considered negative resistance. Probably the only case in electrical engineering where you get a negative resistance. Induction generator. Sleep becomes negative. Anyway, it's a very tricky thing, right? Okay, so if you have no more question, we'll call it a day. Maybe I will wait for some time and then stop the class. All right, then I will stop the recording and stop the class. We will meet tomorrow, 7 p.m. and no class on next Monday. 7 p.m. tomorrow we are meeting.